The other night we learned how to calculate molarity, which is the main way we can quantify the concentration of a solution. Take a look at this picture. In it you can see a volumetric flask that looks pretty concentrated. The color of the solution is very, very dark. And you can kind of guess that maybe in this first test tube it was straightly poured, or it poured straight from the flask into the test tube. But then you take a look here and the solution gets lighter and lighter and lighter and lighter until there's nothing at all. How do we quantify dilutions? How do we quantify what happens when we add more water to a particular solution? And why would we want to do that? Well, a lot of times what chemists do is they start out with a concentrated stock solution, is what they call it, and then they use this concentrated stock solution to make dilutions for different reactions that they need certain concentrations for. And it just makes things a lot easier. As opposed to having to make a big flask of each of these concentrations, you can easily get one from the original. Let's see how we calculate that. Final topic of the night, dilutions. Diluting a solution involves increasing the solvent in the solution. So let's think about a nice tall glass of Coca-Cola that is filled all the way to the top with ice. You fill it up on a hot summer day, you can't wait to get to it, but you get called away, you gotta go clean your room. By the time you get back, all the ice is melted, you take a sip, and what does it taste like? Watered down pop. That's because you increased the amount of solvent in your solution. You increase the amount of water in the Coke, and it tastes watered down. That happens anytime you have ice in something and you leave it for a long time, right? That's called diluting, okay? The decrease in concentration of the solution is what we call dilution. So the relationship between the amount of solvent and the concentration of a solution is inversely proportional. So this is kind of like Boyle's law. As the molarity increases, typically the volume will decrease. And as the volume increases, meaning you add water to a solution, its molarity is going to decrease. It's going to get watered down. We call it diluted. So let's take a look at how we apply this. It's just like Boyle's law. What volume of a 0.15 molar sodium hydroxide solution will you need to make 250 milliliters of a 0.03 molar solution? We do call the capital M molar, and just as a little side note, it's spelled this way, like a molar in your mouth, a tooth. We call that molar. You can also read it as moles per liter if you would like, but we typically call it molar. Anyways, let's take a look. Let's go through this again. What volume of a 0.15 molar solution? So we have our M1. M1 is 0.15 molar. V1, we don't know the volume this time. Our second molarity is 0.03 molar, and our second volume is 250 milliliters. The beauty of dilutions is the unit of volume does not matter, again, as long as it's the same on both sides. So you can be in milliliters or you can be in liters, but both volumes have to have the same unit. Now this becomes a plug and chug situation. So we have M1 V1 equals M2 V2. We need V1, so we're going to divide by M1. So our V1 is equal to 0.03 molar times 250 milliliters, don't forget the decimal, divided by 0.15 molar. Your molarities cancel. You're left with milliliters, which is awesome. Sorry about the molar moving. When we run this calculation through the calculator, we get a volume of 50 milliliters. And we can only keep one sig fig because of the 0.03 molar, so we just write 50 milliliters. of 0.15 molar sodium hydroxide will be required. So this is how you run dilutions. You're going to have lots of practice next week, Monday and Tuesday, to try out all 4 equations and solve various problems in different directions. They're not all going to be this way. But again, I told you before, we're at that point you're going to have to figure these out and problem solve. Have a great weekend. See you Monday.